Hello, welcome to this video. In this video, first we define two types of functions which is defined from one topological space to another topological space. First function will be called open function, and the second type of function will be called closed function. After defining the two type of functions, we will see an example in which we discuss a function which is open but which fails to be continuous. So let's see the first definition. The function f is defined from x to y. A function f is defined from x to y, and this function is said to be open. This function is open if for every open set which exists in X, its image set. You know that its image set is f(o). Under the function f, image of O is can be written as f of O, and that's a subset of Y. You can you have to verify that whether this function the new set, whether the set f of O is open in Y. So if for each and every open set O which exists in X, if f of O is open in Y, then we say that the function f is an open function. This open that openness property of the set is used to name the function. See, open function, or it can also be called an open mapping. In a similar fashion, we can define a closed function. But for this definition, for defining closed function, we have to consider arbitrary closed sets in X. So let us call this set C. So let C be any closed set in X. So we consider here C as a closed set in X. Then its image set is taken, that is f of C. F of C. If f of C is also closed in Y, then we say that the function f is closed, and this should happen for each and every closed set which exists in X. This closeness, that is fc, must be closed. So if for each closed set C in X, if f of C is closed in the second space, that is Y, that's in Y, and we say that the function f is closed. We also say that we also call it a closed mapping. So a closed function, f is a closed function or a closed mapping. Then see the example, the previously told example. That example says that there exists an open mapping which fails to be a continuous function. Here we define a function as an example. Here we define a function f from the set of real numbers, from the space R of real numbers to the space Y, where Y contains only two elements. That is Y equal to set AB. A and B are the two elements in the second space. And how do we define the function? The function f is defined as f of x is equal to, see, x is a member of the first space. X is an element of R. Then f of x is equal to A if the value of x is less than or equal to 0, and equal to B if x is greater than 0. So once again, see the definition of the function f of x equal to A if x is less than or equal to 0, and equal to B if x is greater than 0. This function does map every open set in X. See, any open set you can consider in X, and you can and you can also verify that it maps under the function f. The image of that open set will be and it is contained in Y. It's a subset of Y, but you can also see that every subset of Y is open. See, every subset of Y is open. Since every subset of Y is open, now it is clear that an open set which exists in X is surely mapped to an open set in Y. So the function f is an open mapping. But we have to consider, when we consider open sets in Y, and it's and the effect of the inverse image on that open sets, then we can say that the function, we can verify that using considering that that way, the inverse image of open sets, we can verify that the function f is not a continuous function. How can we do that? So for that we have to consider, see, we have to consider the one point one member element of the or the one member set of the second space Y. See, let's consider a, the element a in Y. When we know that that set a the set a, this is not ordinary a, and we have to consider it as set, the set a. So it should be written as with a should be in a set notation. So set a is open in Y. We can see that set a is open in Y. Similarly, set b is open in Y. But here we consider set a. Then set a is open in Y, but its inverse image, f inverse of a, equal to, see, using this definition, definition of f of x, definition of f, that is f of x is equal to a if x is less than or equal to 0, and equal to b if x is greater than 0. Using this part of the definition, we can say that f inverse of a equal to minus infinity 0. Clearly it is not an open set in R. So this set is not open because of this closed bracket. See, this closed bracket on one side. This set is not open in R. So this is closed. It is not open, and therefore we have to say that the function f is not continuous due to this reason. So due to f inverse of a is equal to minus infinity, the set minus infinity, the interval minus infinity is 0, the close here, which is closed here on one side. So it is not open in R. Okay, that is the end of the example. Thank you.